Good morning, everyone, and welcome to our Topics and Preservation Series presentation for June of 2024. A big welcome to those of you in the room and as well as the 170-odd folks that are with us online. So we're delighted to have you with us today. It gives me great pleasure to talk about this collaboration and partnership that, as you'll hear in the presentations, began before the pandemic and survived the pandemic, and we really have had a lot of joy and intrigue in working through wonderful challenges with this project. So I just wanted to start with an overview of what really puts this in context, because we get a lot of new techniques and instrumentation, and often that's like, what does this mean for collections and what we're analysing with cultural heritage? But each new instrument helps us add new knowledge, and a lot of that is then working with the curatorial and the researchers to understand their questions and how our instruments and our techniques can actually work with that. Part of this too, as you will see, is we create very large data sets. We can't answer a question with one instrument, so we're always pulling together different disparate data sets and how do we actually put them together in a more effective way. And as I said, this interaction with scholars is such a critical part of understanding what we can do with our knowledge and our expertise. The program today is a very rich program. We have four wonderful researchers with us from the University of Nottingham University who will be speaking, and I'm just going to give a short introduction to those. We will take a break at 12 o'clock and there will hopefully be a timer on so you'll know when to come back, but please come on in. Just to start to put a little bit more context here, one of the things we do with our approach to analysing collections is think about how we can capture what's happening right across the surface of whether it's a painting or a manuscript or a pre-Columbian ceramic, and then based on what we can understand with the spectral imaging after mapping that, what's happening at specific points, which are the pigments that are different and or similar, and how can we maximise what we can do with the different techniques. So we had started with this approach, and it's just wonderful talking with our colleagues to understand that we're all actually, whether it's at the Getty or at Nottingham, approaching this in a very similar perspective of how we actually bring together these different techniques and get the most out of our analyses. And so those complementary techniques look at both organic, plant-based, and then inorganic components that have trace metals in those. This is usually the slide that has far too much information, but we start with that spectral mapping, the multispectral imaging, or some of you may know that as hyperspectral imaging, and then we add other specific techniques such as Fourier transform infrared, fibre optic reflectance spectroscopy, X-ray fluorescence, Raman, and other techniques there. We had for many years affectionately called this our Go team, where we start with spectral imaging and then we add on other techniques as we go. And this is really how we've started to evolve the approach, and as you'll see going through today, how the team has taken this steps further into really looking at what that looks like in an online platform and shared program. I do want to shout out two of our curators here in Prints and Photographs and Manuscripts Division who were incredibly helpful in working with us and our colleagues to share their collections and their knowledge. It was really interesting. I was just talking to Sarah yesterday, and just some of the unique insights they knew because of being so familiar with the collections really helped us understand and sometimes go slightly different. And we did look at around 100 collection items, which was quite a lot. So with that, I want to give a big shout out to PRTDD staff, Megan Hill, Cindy Connolly-Ryan, Amanda Sartorius and Chris Bolsa, working together as a team, as well as everyone else in PRTD who helped with watching things, organising things, standing in and sharing and bringing all of this data together and working with our colleagues. So I wanted to keep my introduction short to make sure we have plenty of time for our wonderful researchers to talk. So without further ado, I'm going to invite Professor Heide Liang to come up and start her presentation. Professor Liang is a distinguished professor at Nottingham University in the Imaging and Sensory Lab for Archaeology, Art History and Conservation, which you will now hear and refer to as Isaac. So without further ado, I'm going to hand over to Heide. Please welcome her.
Thank you, Fenella, for hosting this here. This is one of our dissemination events as part of the project. So I'm from Nottingham Trent University, just a slight correction. And I'm here with three of my colleagues who will talk afterwards. I will introduce them as we go along. And so this project, From Lima to Canton and Beyond, an AI-aided heritage materials research platform for studying globalization through art. It's a project that has been, I think, more than 10 years in the planning. Now thinking back, thinking back, you realize that isn't something that just happened. And it's one of the I suppose benefits of Brexit, that is, there's suddenly funding for collaboration with the rest of the world. And so one of the initiatives was the joint funding from the NEH in the US and the AHRC, which stands for Arts and Humanities Research Council in the UK. So NEH is a National Endowment of Humanities, right? The joint funding as a core, part of a core for new directions for digital scholarship in cultural institutions. And here we have, I was amazed at how much enthusiasm I received when I suggested this idea to colleagues around, in the UK and in the US. There's half a dozen in the UK, half a dozen in the US, roughly, cultural institutes that decided to partner together to do this work. As you can see and we have advisory boards that includes art historians, curators, historians, and etc. And that's giving us, leading us to which collections to look at, and so on. And as you can see that there's two parts. Just by looking at the title, there's two parts to it. One is answering some arts and humanities questions. So from Lima to Canton and Beyond, studying globalization through art, right? And in order to study that, we as scientists are trying to analyze the materials using various scientific techniques, as Fenella has already introduced. So to aid us in working out what materials are on the artworks, we also need AI to help us, because we have, as you will see, that we have large collections to deal with and huge amounts of data with non-invasive imaging and spectroscopy techniques. So we are cranking up lots of data because it's easier to do these days. But then what? You have to analyze them in an efficient way. And this is the topic of part of the other strand, the science strand, to this project, which is going to be covered by Soteria in the next talk, how we actually do that. And so, talking about the history, how did we come up with this? Actually, I have to go back about 10 years, and I managed to find this slide. It was a joint talk at International Institute of Conservation in 2014 in Hong Kong. It's a joint talk between myself and Lucia Bergiu at VNA. And at the time, we had a project funded, again by AHRC, called Culture and Trade Through the Prism of Technical Art History, a study of Chinese export paintings. And this project was kind of also suggested by a VNA curator. So when we studied this project, we were looking at, first of all, just a word about Chinese export painting. So there were workshops, just like a factory, producing watercolors for export in the 19th century in Canton. This is 1859, the Illustrated London News, where they showed how in one of these studios you have so many craftspeople trying to paint these watercolors. They are usually for export in the sense that either they are made for the travelers who came to China, or they are made because they're commissioned, for example, as botanical records, scientific records. And in that project, we actually looked at two particular collections. And one is a V&A collection, which there's about 20 selected for us to do this. But the provenance and when it was produced was not as clear as the other collection that is kept at Royal Horticultural Society. It's a John Reeves collection, and it was very good provenance, and it's dated 1817 to 1831. And they were mostly commissioned as scientific record of plants in southern China. Because of the Royal Botanic Gardens were interested in that, and Horticultural Society were interested in this kind of scientific record. So we studied this, and just to give you and in fact, we are still using the Reeves collection for this project for comparison. So here is an example of a commissioned botanical drawing as a scientific record. You can see that it's not just a pretty picture of a plant, but at the bottom there you have also the little leaves drawn separately and so on. And so then we did the material analysis at the time so if we concentrate on the Reeves collection, what we found was that because they are commissioned, so the craftspeople and the artists had to draw, paint on Western paper. Most of them were Whatman paper, and occasionally they did some on Chinese paper. But presumably the one that's going to be that was sent back to archive was actually on these standardized Western paper, and also we found that the Western paper were not sized the same way as Chinese paper. And the other thing we found out was unusual for Chinese painting was a graphite was used for preparatory sketches. However, there's no evidence of imported pigments used. We know that the red insect dyes, scale insect dyes were used, but of course with non-invasive technique, we cannot be sure whether it's cochineal or not. But we didn't find any evidence for Prussian blue, for example, even though that we knew Prussian blue was at that time imported into China. And the other thing is that then we thought, okay, maybe we can compare one day. Back then, we said one day we can compare these materials found on expo paintings to that of mainstream Chinese paintings that's meant for the domestic consumption, and see if and also the way they painted, is there a difference or not? Because actually, if you think about mineral pigments like vermilion, you can just about red ochre or whatever, you can find it in every culture throughout history. So that by itself is not very interesting. What's interesting is how they use the pigments, how they combine the pigments to achieve a certain color. That you will have variations between the cultures. And so that's where we look at it carefully, rather than listing, these are the pigments that was used, but actually how, for example, they combine a yellow and a blue, what kind of yellow and blue together to achieve a green. So that's the kind of interest we had. But luckily, when we started this project, it also happened to be that the National Museum Asian Art, or used to be Freer Gallery, they had published a book based on more than 10 years of studying of their collection of Chinese paintings. And these are what you might think of mainstream Chinese paintings for domestic consumption. For example, paintings by scholars, court painters. But of course, there's also a small selection of paintings for religious purposes, like Buddhist paintings. And also some ancestor portraits, which are a little bit different from the fine art paintings, shall we say. So they actually studied this and published this book, which is very timely for this project, which meant that we can actually do the comparison quite easily. And by the way, they won the AIC Publication Award this year. And so congratulations to my colleagues at NMAA. And some of the work we did 10 years ago is the publication down there. If you're interested, you can look into that. And so by comparing with what they published at National Museum of Asian Art, we found that actually the way the pigments are used for these export paintings are not very different from what you find on mainstream Chinese paintings. Certainly, for example, even though they are painting on Western paper, here is an example from the talk that we gave 10 years ago. So if you look at green leaves, most green leaves were painted with a combination of malachite, gamboge, and indigo. And it's interesting that if you look at archival, contemporary painting manuals, and there were lots at the end of 18th century in China. And so Mustard Seed Garden Painting Manual, which is famous and is translation in English as well, it says that when it talked about painting leaves on paper, it says the base layer should be malachite, and layers of gamboge and indigo on top. And another scholar, Shen Zongqian, said in 1781 in another painting manual that he said inorganic pigments are more color fast, which is good. But organic pigments really give that more vibrant color. And so by combining the two, you get advantage of both. And in fact, we found on these paintings that on the bottom they have malachite, which is an inorganic pigment, but on top you have the organic green, meaning a combination of gamboge and indigo. So actually, what we are finding on the paintings matches up very well with painting manuals of that time, which is interesting. So these are the kind of things you can do, of course, plus what people are finding on traditional mainstream Chinese paintings and materials in combination, we're saying, well, they're quite similar, actually, at least for the Reeves collection that's meant for the West, except, even though they're painting on Western paper. The only painting technique that's different, they use graphite to do the underdrawing or the preface sketches. Now, at the end of that project, I came across this article, From Lima to Canton and back. 19th century Chinese watercolors for Peru by Barbara Anderson. And she wrote this article for an exhibition that was held in 2011 at Museum of International Folk Art in Santa Fe. And it was called Folk Art of the Andes. And I just came across that by chance, and I couldn't believe it after I read this paper. What? You mean these Chinese expert paintings, they were not just painting the Chinese subjects, but they're painting Peruvian subjects. And not only that, what she was talking about, Barbara Anderson was a curator at the Getty Research Institute, and she found similarities in designs between a collection at Getty that's attributed to this very important 19th century Peruvian artist, Pancho Fierro, and those ones at the Getty were painted on paper. But the ones at Santa Fe, they were painted on pith, but with almost identical design, and which you can see there. So they are. I'll talk about pith in a minute. It's a substrate, plant-based substrate that looks very much like silk, and that's why they use it, and it's cheap. And it's framed with blue silk frame, as you can see here. And the subject matter, you can see that they like these exotic figures of the Tapada women. They wear these headscarves that shows just one eye. And one of the quotes from from Europeans writing about it is that the mysterious tapadas could flirt with impunity, and their upper body and faces covered except for one seductively exposed eye. So that's what you see here. And so she was writing this article and talking about it, and I was fascinated. I thought, well, we must study this, because how could it be that people could do this? You know, this is maybe copy from the Peruvian design, and then somehow it found its way back in North America. So how did that, why would people actually even bother? That, I had loads of questions. I really wanted to study that. And by reading that article by Barbara Anderson referred to an earlier exhibition held at what's now Hispanic Society of America. And that exhibition was in 2006, and it's called Reproducing Nations, Types and Customs in Asia and Latin America, in the period 1800 to 1860. And I would like to give a quote of an interview that Natalia Machluf, who is a former director of the Museum of Art in Lima, when she wrote all these essays for the exhibition. And that actually made me realize why it is that I never heard of it. When I was working on Chinese export painting, I spoke to all the experts on Chinese export painting, and nobody mentioned this. They were unaware of what's happening in the Americas. Whereas there's been 2 big exhibitions of that over here. So it seems that the world today is not as linked as it was back then. So what Natalia said was that scholars of Chinese export art are perfectly aware of the impressive output of Chinese workshops and their remarkable capacity for reproducing objects of all kinds from around the world. Nonetheless, while European and North American trade with China has been the subject of intense research, and while the art produced for these markets has also been extensively studied, the same has not happened in other regions. So that explains why I didn't know about it, and when I saw it, I was so surprised when actually these things happened 10 years before the earlier projects. And the role that South American Pacific ports played in this network was significant even before independence from Spain. And the reason why they refer to that is because when it was under Spain, it was very restricted trade and so on. And the evidence for such large numbers surviving export watercolors Peruvian subject certainly testifies to intense level of trade in the first half of 19th century. The trade route intensified in the late 1840s when the importation of Chinese indentured laborers became the mainstay of large plantations on the Peruvian coast. So there, when I read that, I thought, oh, how do we know it wasn't done by some people over in Peru? The Chinese who had already migrated there. So there were lots and lots of questions that made this whole project very interesting to explore. And so here are the connections by picture. You can see that the first pair, the left-hand side, is one of the tapada dressing and how they put the veil and the skirt on and so on. And that's from the Hispanic Society of America. And on the right-hand side, so the left-hand side is believed to have been painted on paper most likely by Pancho Ferrero. And the right-hand side one is one that is from the Library of Congress collection. And it's painted on pith. And it's even attributed to the Studio Tingua, one of the very well-known Chinese export painters and his studio. And the dates are based on the styles and whatever was believed to be 1830 to 1840. So, and then you have another pair on the right, the Peruvian watercolor on paper. On the left is from the Yale collection. That collection, Hispanic Society collection, goes back to the same collector, some of them. And on the right-hand side is a very similar design on pith that's kept at the Lilly Library, Indiana University. You can see how all our partners came about together, right? Linked by collection. And talking about pith, Now, we analyze these paintings on pith about how to make pith as a substrate for the pith paintings, because that's interest, presumably, of Royal Botanic Garden Kew, and it's kept in Kew's Economic Botany collection. And you can see pith is a plant, and then they take it off and slice it into thin slice to make the substrate. And it's very shiny, and what's very interesting we discovered was that for some of the ones that's not mounted with a backing paper, you can turn it around and see what's happening on the other side. And when I saw that, I thought, oh, this is definitely painting in the Chinese tradition, because it's well known that silk paintings you would paint at the front and at the back. For example, for flesh tone, the face, you would load more pigments at the back of the substrate, like silk, to make it opaque, so that at the front you don't have, with a similar color, of course, at the front you don't have to load with heavy paint, and so that it looks much nicer and translucent and so on. So you paint at the back and paint at the front for silk painting. And they obviously treated pith in the same way they treated silk, and they painted in the same way. So there's no, no doubt that these were made by somebody trained in the Chinese style of painting. And on the left, that's a painting from the collection at Museum International Folk Art. On the right, these are from the Lilly Library, Indiana University. And so, we want to study the global connections through art. And we chose a period, 1780 to 1850. There's all kinds of reasons for choosing that period, which I'm not going to go through them all, because one of the things about stopping at 1850 is also partly because after that, photography became more and more important. And I remember that the reason why these botanical paintings were recorded in this way is because initially they tried to bring the beautiful plants from southern China to England, but they had to go through the Horn of Africa and all that, and after such a long journey, going through different climatic conditions, the plants all died. And they decided it's better to record them. But of course, they don't have a camera today, and so they had to draw them. And so why this sort, actually this kind of, as you've seen that people like Natalia and Barbara Anderson had realized that this is a global, the curators have realized this is a global phenomenon. And this phenomenon is inspired by Enlightenment, just like how museums came about as well, right? And Europeans and North Americans were, at the time, able to travel a lot around the world. And they were collecting scientific information from around the world through botanical drawings, ethnographic types, mapping the world, and so on. So our job is, as scientists, our job is to go and analyze these artworks or scientific records, and in polychromy, I guess. So analyze the artist's materials in order to answer a series of questions, which can then in turn address the broader historical questions. So through analyzing artist materials. So for example, we're going to look at what are the differences in the artist materials used in different collections of the watercolors. What are the differences in the pigment combination, let's say, rather than mixture, because sometimes it's layered, and painting techniques? And are there differences between the geographic location, the genre, and the purpose of the watercolor, whether it's commissioned or not? And also, is this a collaboration between the Europeans who lived there at these places with the local artists, or completely commissioned for the local artist to do whatever they want? So we have enough in our selection collections, hopefully, to answer some of these questions. And so the artworks. Paintings for export from a region. So when I say paintings for export, they could be either commissioned or the local artist did it in order to please the ones who are going to buy it. That is the travelers, right, from outside the region. So We've included ethnographic ones, which have the Chinese types, the Peruvian types, the Iranian ones. This is where, what Fenella was saying earlier on, it was so useful to speak to the curators at Library of Congress. We would not have known, we suddenly expanded the Lima to Canton and the beyond part, right? So we had some Kaja paintings included now. And then there's Colombian ones that came from Royal Geographical Society, and we are hoping to access some Filipino ones, because those ones are the ones we actually found out more recently. So we keep finding out more of what's happening, this phenomenon. And then the botanical ones, which some of them are commissioned by East Indian Company, and others are from the learned societies in England. And so there are ones from India, from China, and from various places in Southeast Asia. And then we also, as I said, wanted to compare, for example, between the different purposes, the Chinese painting for domestic consumption, the fine art categories, the portrait ones, which could be ancestor portrait, which may be done by the craftsmen, the same kind of craftsmen who do export paintings. Is there a difference there? And also we have military maps, that's meant for the Chinese Navy, so at the time. And so again, there's different purposes. We can explore a little whether they do things differently at all or not. And so here's a map of the origin of the artworks then and now, in the sense that the red stars are where they were made, and the blue parts are where they are now, in which collections. Okay, so I'll give you a summary of the different collections involved. Even though Yale University Art Gallery is not officially a partner here, but because they have relevant collections, they're kind enough to let us have access. And we just kind of keep on bringing in new collections into the equation as we go. And so some examples that we are going tonight to New York. And some of our instruments are already there set up, that we are going to work at Hispanic Society of America to look at their collection. And they are, of course, very, very interested in Pancho Fierro's paintings. And so here there are some examples. And on the right-hand side, they also have some drawings from the Cantonese copies, on pith. And then here is closer to home, a Library of Congress in this building. We have the watercolor on pith. There's some samples of them. And they are all Peruvian subjects on pith. So these are interesting because apparently there's a note inside the cover of one of the volumes, and this is direct copy from the catalogue. These watercolors are made by a Chinese artist between 1830 and 1840 after Peruvian drawings provided by Mrs. William Wheelwright. So obviously there was this woman who is likes very much the Fierro style of drawings, and so much so that she would have the templates sent to Canton or Guangzhou today, and to have them made into the pith copies and brought back to her. So that's very interesting, and it actually traces to the studio of Tingua as well. And the examples that I think Sotir is going to talk about is the Getty Research Institute. These are attributed to Pancho Fierro, and that was what Barbara Anderson was talking about. They were on paper, and you can see a sample of them. And also the Santa Fe one, that's on pith. Again, a sample of these. You can see already there's very similar designs. And also that in our previous collaboration with Royal Horticultural Society and V&A, we never analyzed any paintings on pith. So we needed to analyze them on pith to see if they do something different on pith compared to on paper or not. And so this is the collection of Royal Botanic Gardens at Kew. So these are on pith, and it says unknown artist Chinese school. That's all we know, early 1800s. And then we also have some that's on paper, and they were produced in Penang and produced in Hong Kong. So you are expanding into Southeast Asia. And also, I was very lucky to have access to a couple of items that made it into the Forgotten Masters exhibition at Wellcome Trust. And Wallace Collection. They were putting up this exhibition just before the pandemic, and I remember going to it and seeing this. If only I can analyze these and see what the connections are, and then to be able to do that was really a privilege. And so these are from the Royal Botanic Gardens, and these are the unknown Bengal artist that was commissioned by East India Company to paint the plants and so on. And also we have a collaboration here, because Royal Geographic Society has the Joseph Brown collection. Joseph Brown is a British trader who lived in Colombia between 1826 and 1841. And he collaborated with local Colombian artists, for example, the Castillo brothers, who colored some of his drawings. So this is really a collaboration. And he seems to have maybe copied Jose Manuel Groot's drawings as well. And so these are some examples here that we also analyzed. And it's interesting that they seem to have some gum varnishing going on there. So it's very different from all the other but then it's also a collaboration, I guess. And the pigment that we found here is also very different from all the other ones, and probably more akin to the English ones at that time. And then this is another one from the Library of Congress, and that's the one that the curators told us about, and it's exactly the right kind of dates that we're interested in, 1830s, and these are done by local artists at Kaja, commissioned by Justin Perkins and the American Missionary. And so we've included that in the collection. And the ones we really want to get our hands on is the Sino-Filipino export paintings that we discovered very recently. And the left one is from the New York Public Library. I hope at some point we can have access to that. And so Justiano Asensio and Damien Domingo are two well-known Filipino artists of Chinese heritage. And they paint in a kind of Western way, as you can see. But what's also interesting is that in the article that was, it was Natalia Majlov who actually pointed me to this article by here at the bottom, where they showed that you have these painted on paper, but you have copies painted on pith. So that's kind of interesting because the Philippines was part of the Spanish Empire, of course. And could it be that these, this is my thinking, we don't know, could it be that these Filipino artists of Chinese heritage, based on their connections back in China, had thought about having these copied, and then maybe the South Americans coming over to Manila are seeing these things and gave them idea that this could be done. I wonder. I don't know. And we hope we can find clues. And finally, as I told you, that the National Archives has this collection, large collection of Chinese military maps on paper from the 1850s. And these are confiscated because that was the first Opium War, the British won, and so they confiscated this military map from the Chinese. And then they have quite a few of them, and we've analyzed these as well, just to see that for a different purpose, how do they do it? Is there any difference in the painting techniques and material use or not? Now, that's the background to what the whole project is about, why we are interested, right? And now as we said, as Fenella had mentioned as well, is that we have so much data. And I talk to colleagues around the world, especially large museums, large libraries and archives. Everybody says, yes, we don't have an instrument problem anymore. We have lots of instruments. But these instruments are producing such a volume of data. What do we do? It's going to last us a lifetime if we analyze them the traditional old way. And so it's not surprising that we, at a similar time, that I think we started this project at we're going from Maritime Silk Road to land route, okay? But that's not the main point. It's about how we got involved in developing the tools. And this project with Dunhuang Academy started in 2011, and it lasted about 7 years that we worked on these cave paintings. Initially, it was us bringing the latest instrument that we produced to try it out. And then it went into some more interesting research questions we addressed. And here we managed to scan with our spectral imaging instrument. So on the left, you see that. We call it all cave remote spectral imaging. That's just me, because I used to do astronomy, and we have all sky survey using spectral imaging. So, but here it's all cave survey, but essentially it's the same thing. You automatically scan the ceilings, right, instead of the sky. So you can do that automatically and produce all these spectral imaging data, and then that particular instrument has 10 spectral bands between 400 and 850 nanometers, roughly. And the aim of that is to get high spatial resolution, but you want it to be fast, and you sacrifice a bit on the spectral resolution, which is not a problem for majority pigments because they don't have very sharp absorption lines. So, but when you are interested in whether it's madder or lac or cochineal, then you're interested in slightly higher spectral resolution. And but otherwise, as a survey instrument, that's perfectly fine. And then because we realized the huge amount of data we are getting, we then started working with a stats colleague who helped us in working on a way of analyzing the data. So we went to her and said, is it possible that we can automatically gather all the pixels with the same spectral response together in a cluster? And then that culminated in machine learning methods to do this, to automatically pick all the pixels with similar spectral response. So that essentially gives you the idea of a material distribution map. You'll hear more of this from Sotiri's talk, who actually worked with a stats colleague to develop this technique. And then we then, based on the material distribution maps, we can strategically decide where to do our point-based analysis using complementary spectroscopic techniques. So then, since we said, okay, fine, we can do this for a building now, yeah? But we can apply the same technique to an entire collection. And this is where Luke Butler's PhD started, in collaboration with British Library. And we had the British Library curator, Annabelle Gallop, who was very enthusiastic about this idea. And so his PhD project is called A Study of Maritime Silk Road Using Scientific Imaging and Artificial Intelligence. And it's to look at the whole collection of illuminated manuscripts from the Maritime Southeast Asia collection in the British Library. And he did exactly that. And you can see that which islands and some of the manuscripts came from, and to be able to analyze and understand. So you can see that you can, after this kind of machine learning-based clustering, you can go from billions of spectra, reduce that to so there's billions of spectra for thousands of image cubes, and you can reduce that to a much smaller, manageable number of distinct spectral groups. And then you have the mean cluster spectrum, representative cluster spectrum for each of the cluster to make life much easier. You reduce the amount of data you have to deal with. And so in parallel, we had another project also that was a call just before the call that funded our current project. And that was a trial one from Arts and Humanities Research Council in the UK, trying to see how to develop partnership with US to fund these kind of collaborative projects on digital scholarship. And that one was called AI for DigiLab, a new concept in digital infrastructure heritage materials research. It's a much shorter project, only for 1 year. It's focused on the tools only. And that one, we had collaborators from the National Gallery, the National Archives in the UK, and in the US, we had IPCH from Yale, Getty Conservation Institute involved. And so we then developed some of the tools to do the clustering. No, we had a clustering code already, but it was about improvement. And then we realized we need to visualize them easier because at the time, a lot of places are finding it difficult to even interrogate image cubes. And I guess it's still like that today, even though if you have more money, you can buy the NV software maybe and play with that. But if not, you're still stuck, right? And so we developed these tools to allow you to interrogate image cubes, and we are going to distribute them freely for the community, because it's all about sharing tools. And today we talk about linked data, that's open access and all that, so we're all going in that direction, right? And the tools you will see later shows that even at data collection stage, we are already trying to link our data together. And so that's that project, and after that, of course, it's this project. So I've given you the whole history of where the project came from. Now, so you realize how we as scientists can help in answering these history questions and so on, arts and humanities questions. And so before I go on further, I just wanted to introduce my lab and why we are in this at all. So the Imaging and Sensing for Archaeology, Art History and Conservation Lab, Isaac, of course, Fenella's already said it, so I didn't have to say a whole mouthful of that again. So we, Isaac Lab at Nottingham Trent University, we do, broadly speaking, two types of things. The first is to develop new instruments tailored for heritage applications. As you know, that you buy a commercial instrument that might be for medical imaging. Sometimes it doesn't immediately translate, and you have to adapt it or whatever. And sometimes it just simply doesn't exist, something that really help our community. And so we build novel instruments, and some of these instruments, they are actually, from the optics community, an instrument development point of view, are also at the forefront. And so that's also an argument to say that cultural heritage-driven research can produce instruments that's applicable to other fields. We are not always the ones that borrow from other fields. We also invent and produce things that's useful for others, because industry sometimes do come to us and say, okay, that instrument of yours could be very useful for us. Yeah. And so we developed those instruments, specific cultural heritage research. We also then, of course, as we said, that with instruments is not enough. When you produce the data, the way you analyze them can make a huge difference. And so that's why we also develop new data science methods to drag the information we want. Again, you need to know the context. So what is the information you want, right? And so that's what we do on one hand, but on the other hand, we do apply it to archaeology problems, art history problems, conservation problems, because it's our interest. And not only it's our interest, it also helps us in going back to make better instruments and better data science methods as well. So it's a positive feedback loop. And so I just want to give you some highlights of our latest developments, just to give you an idea of the kind of things we do. So I've already introduced the PRISM system, which is a remote 3D spectral imaging for large area survey instrument. That instrument, okay, hang on. Right. So that's the instrument surveying a Carolingian, a church with Carolingian wall paintings in the Swiss Alps. Okay, so we can automatically scan and get the spectral information. As you can see, that the spectral image cube means that you have spatial information, but also the third dimension is spectral information. And so each pixel, you will find a data point. So if you have 10 channels, you have 10 data points to give you a spectrum. And in this case, it's identified with a reference indigo spectrum. And then, so you can do pigment identification there. But at the same time, because every time when you take an image, you have to focus. If you're focused, you know how far it is. You can read off the focus position and find out how far away that point is. And of course, you know in XY angles where it is. So you have the 3D point cloud for free. And of course, the other one, which is more obvious, is that if you have in the visible, you have the spectral information, then you can automatically derive the color information for any lighting conditions you want. And that's the most accurate way of doing color, capturing color information. So that's one of the things we do. I mean, that's quite old now. The first publication, I think, was 2007, and then a more involved, comprehensive publication was 2014. And however, more recently, in the last 5 years, we started expanding these remote sensing techniques for obviously heritage sites and so on, and so that we can do remote Raman spectroscopy from the ground at a distance of 10 meters, for example. We can do remote laser-induced fluorescence hyperspectral imaging from the ground at 10 meters as well, and so on. And with the PRISM instrument I showed earlier on, we have actually used it up to 30 meters. And also we have targeted smaller area surveys, also in the remote mode with telescopes and so on, that would give you hyperspectral imaging from 400 nanometer all the way to 2,500 nanometers. So to give you all the, imagine doing fiber optic reflectance spectroscopy, but you do imaging and at a large distance without scaffolding. And then the other area, which is more, the remote instruments is also very useful for collections as well, because it's so very convenient to take it somewhere. You can put it in the middle and it scans. Right, you don't have to have a electronic easel or anything like that. You can just do that, and then you have the you can correct it for the geometry later on. That's just a mathematical transformation. And one that is more applicable to collections is our work on optical coherence tomography, and that's the latest development in a PhD project in collaboration with the National Gallery in London. And there you can see that you can scan with this microscopic technique to see the subsurface microstructure and see layers of paint using that. And then we had this one is supposed to be helping conservators to decide how much further they want to clean the varnish from the paintings, because sometimes it's not clear whether it is a glaze layer or a varnish layer. And so we combine it with microscopic hyperspectral imaging. So it's a combined system. So with the same white light laser, you can use a visible part for the microscopic hyperspectral imaging and the infrared part for optical coherence tomography. And they're co-aligned so that at each point you know how thick the layer is and what the reflectance spectra is. And based on that, you can extract spectral information. In this case, you see that's a yellowed varnish, not a glaze, so you can keep cleaning, something like that. And then we also, a month or two ago, just developed further into the long wavelength OCT to the mid-infrared, because for opaque enamels, and these Chinese enamels or 18th century enamels tend to be quite opaque. Using this technique, you don't see that far. So here it is, one at 1.3 micron wavelength OCT. You're not seeing very far, but we just recently developed this one at in a mid-IR, 3.7 microns OCT, and then you can see the structures and what's going on inside the enamel much clearly, all the way down to the copper base. So these are the sort of things one can do using modern imaging techniques. And of course, we want to share this with everyone by putting them, all these instruments, into a mobile lab. So the Isaac Mobile Lab has our in-house developed instruments, plus some of the commercial instruments that everybody uses as well. So because it's sometimes a trade-off between whether it's practical to move something or the best instrument for doing whatever. And so we are part of the European HS and the European Research Infrastructure Heritage Science, so that people apply to us, and then we go if their proposal is successful. So we go and with our MO lab to work with people. Either they don't have the expertise or they don't have the instruments, or both. And that's our van, for example. And so where have we been? So we do go around the world, not just in Europe. So I'm just letting you know, so that if you have a very exciting project to talk to us, maybe we can come. And so then back to the project. So we selected a few instruments for this particular project because we have to travel over here. The van won't take us here. I wish. And so we had to fly, and then we have to be careful about how big the instruments are to bring it here. And that they have to be carried safe, because 10 years ago we went to Brooklyn Museum with our OCT, homemade OCT, and FedEx, and that was scary. So since then, I said, never try that again. We're going to carry the sensitive parts with us, like the optical head or whatever, and things like a mount that scans, it can be checked in and all that. And so we, last time when we came to DC, we brought a spectral imaging system, the PRISM system I told you before with 10 bands, but not for remote. We'll get rid of the telescope and put a more normal lens there and scan at 2 meters, but it's automatically scanned on the rotation stage, pan tilt stage. And we complement that by also our in-house developed Raman fiber optic reflecting spectroscopy combined system. And the Raman is also designed in such a way that you can do offset Raman as well, if you're interested in the deeper layers. So that's what we brought. And when we were here, that's the only, the Raman Force combined system, the only one we brought here, because we only had a week in DC. So the rest of the team were over at the National Museum of Asian Art with the spectral imaging system PRISMs, the XR point analysis equipment, and FTIR doing that. And then we afterwards went over as well. So whereas here, we also had colleagues here at the Library of Congress helping with using their instrument. I'll talk about that in a minute more. And so time is the issue on field trips. You can't be perfect. And efficiency means budget. And so far, we've analyzed about number of watercolor imaged is 320-ish, and we've collected 3,600 spectra of different types, and then that's a breakdown of different collections, what we did. You notice at the Library of Congress we did most of them, because Fenela's team, there's 3 of you working on it. And they were working on it even after we left. So they can do it at their leisure, right? And so I just wanted to say that this is working together, putting resources together. So we have, I've already mentioned the Library of Congress. They had their spectral imaging system, XRF and FORCE, to complement our Raman FORCE combined instrument. We worked together, 5 of us from 2 teams. For a few very intensive days, and even after we got back to the UK, they were still working on some of it. And then down the road, National Museum of Asian Art, we had our mobile lab there when we were there because they were still setting up some of their latest instruments. And yesterday I saw that they got their macro XRF scanner going. And so just before we came, they actually scanned a couple of paintings that we analyzed before and sent us the data, and we were using our new tools to analyze them. So you see, it's very good that even though we are not here, and it's much later than the time that we did the analysis, people can still catch up and do other things and combine the data. And then we have another example, which is kind of odd, with Museum International Folk Art. Over there, they had bought a lot of new commercial portable instruments, but they only had one conservator who can operate one or two of those instruments, not all of them. And we heard about that just before we went with Lin Li from Getty. At the time, she was at the Getty Conservation Institute. And I said, okay, if that's the case, I don't have to take my tracer, Nabucco tracer anymore. We just go. And we took our spectral imaging system, but because we said, okay, they have most of the other stuff like force and so on, we have room in our luggage to bring something else. We can bring our OCT with us. And so that allowed us to have, expand the techniques to do things. So, and then we also are going to Hispanic Society of America tonight. And a colleague of ours is already setting up the instrument, but there, because they don't have any scientists there, and so it'll be a standard MoLab access, like what we used to in the European Research Infrastructure PRNHS. So we, with our instrument, our people go and do the analysis, that's it. So there are many guises you can combine these things to pull resources together to do things. And just to give you, so just to show you, we brought OCT and it was useful because not every single painting was unmounted at the back, so we only had one that we can access and see. And we noticed with OCT, without contact, a few centimeters above the paint surface, you are able to do a 3D image cube like this that shows the layers. And then that's a cross-section just above. That gives you also the cell structures and so on. And you can see that there are parts that are painted at the back of the pith, and there are the parts that's black, meaning there's nothing between the pith painting and the backing paper. So you can see that. And here is the same image cube, but you can cut it from top to bottom layers, rather than have them in cross-sections. You can see it like that as well. And then as it goes, you can also see when the drawings appear. Okay, so now coming back to tools, so outcomes. I'm going to wrap up so that I have my colleague describing that in more detail. So that was our initial workflow from the proposal. And we were talking about how to link with our arts and humanities researchers and to select objects, and then how it is that we will do our scientific analysis workflow, which I'll leave it to Sotirio to talk about. And then after we've done that, we can then feed back into in an online environment to collaborate with our colleagues from different domains, and it's a loop that goes around. And then I could also feed into physical and virtual exhibitions and research outputs in other humanities. So that's a new workflow, and that's published in the latest Studies in Conservation issue, which is going to also form our presentation at ISC 2024, which is held in Lima. It's like somebody planned this, isn't it? Last time when we finished our Chinese export painting project, it was presented in Hong Kong, which is very close to where the studios were. And now this time, it's going to be held in Lima, where some of these objects are from. I can't believe the coincidence. So So we developed these tools, GUISI and MAPSI. GUISI helps us in analyzing spectral imaging cubes so that you can do simple analysis with it, even if you don't do anything sophisticated. Just take a spectrum from a particular area and so on. They can do that. It helps you to visualize the spectral image cube also through more sophisticated means of material distribution maps. And then MAPSI is one that was more recently developed that allows us to use it during data collection. So last time we came, we didn't have that. This time when we go to New York, we'll have that, so that when we take the data, we will be able to link the data already. But Soteria is going to talk about the details. And then in the end, when we got all our data, we processed, calibrated them, and analyzed them. We can also use it as a virtual environment for collaboration with curators and conservators, our colleagues doing the conservation science, and so on. So these are just three screenshots of what these are. And for GUISI, because it developed a while back, there is a simple tutorial video on our website. And this is MAPSI. So at the moment, we're not distributing them yet. But at the end of the project, we will. So watch this space. And next Thursday, if you're in New York and want to see our instruments, how we actually work together, you can come to the Hispanic Society of America. And that's it. And finally, the acknowledgements. There's too many to list. And yeah, so thank you. So next, we'll move to my colleague. Soteria Kugo, who also I mentioned that she already contributed to some of this work during her PhD, which is a while back now. And now she is an academic fellow at Nottingham Trent University, still in the group. And so.
I'm happy for that.
Oh, good to hear. Okay.
Okay. Hello, everybody. And thank you a lot for having us here. So in my talk, I will try to focus more on the workflow that we developed for the analysis of large collections. So after Haida's talk, I don't have to try to explain why we need to analyze large collections of paintings. Obviously, within a specific collection, we can get information about the art history of a single collection, but also by comparing different collections, we can get broader information about cultural exchanges, trading, and historic links between different areas of the world in specific times or through the history. So the importance of analyzing large collections is obvious. Then, as everybody knows, even to extract accurate conclusions about even a specific collection, you need to scan lots of objects in order to have a large statistical sample. And the challenge that arises how you can do that in a time-efficient way. So, as Haida described, in our lab, we have a variety of non-invasive analytical instruments, from spectral imaging to point analytical techniques. We also have developed through the years lots of different techniques for the analysis of these scientific data sets. Some of them include machine learning, some others are more simple data processing methods. And we have also a group of people that they are quite experienced in the interpretation of the scientific results from all these different modalities. So, as I said, through the year and out of necessity and the resources and the large data set that we have collected for different projects, we came up with a specific workflow, which is what I will try to explain through my presentation. But I want you to have an overview of this workflow. These are the different steps. First, we start with the spectral imaging of large collections. The next step is the automatic clustering of this large spectral imaging data set. And the aim of that is to highlight areas that should be examined further. The next step is to apply multimodal analysis using various point analytical techniques on representative of each cluster areas. And the final stage is the complementary interpretation of the machine learning outcomes and the point analytical techniques of the representative areas in order to get the material identification. I will go through each of these steps to make this clear. So, starting from the spectral imaging of large collections, as I mentioned, in our lab we have a variety of spectral imaging systems, from reflectance spectral imaging systems in different spectral regimes, from the visible near-infrared to the shortwave infrared regime. And the uniqueness of our instruments is that they allow us to have automatic scanning of large areas. And we all know that the reflectance spectroscopy in the different regimes, they give us molecular information. But we lately acquired also a macro XRF scanner that can be used for scanning of not very large surfaces, but let's say medium-sized areas, and it provides elemental information. So Haida already spoke a little bit about the oldest spectral imaging system that we have in our lab, which is what we call PRISMS. Is a spectral imaging system, a reflectance spectral imaging system in the visible regime. It's a filter-based system. So basically, what you do is that you point to a specific area. We have 10 filters. The filter wheel goes around, and you can acquire the spectral bands in the different filters. As you see, and as you already know, the further you go to the infrared, most of the pigments and the colorants become transparent, so therefore you can have the revealing of the original sketches. But also, by combining all these images together, you have the so-called spectral image cube, and in a pixel level, you can get the reflectance spectrum. Even though for this system, the spectral resolution is not that high, we know out of the survey that it gives you enough information to assist with the pigment identification of most of the traditionally used pigments. Of course, it faces limitations with the identification of most of the whites, apart from the yellow ochre. And of course, when you have red insect dyes that have fine absorption lines in this spectral regime, this spectral information cannot be used for the identification. However, even though it cannot give the identification, what we've noticed is that it can distinguish between the different pigments. And this is very important information for the next step of our workflow. So here is our spectral imaging system in action. So when we say that we can do automatic scanning, you can see that we have our spectral imaging system located in a fixed position, and the whole system is attached to a mount. So what we do is that we go to a specific location, we acquire our spectral imaging cube, and then without moving the system relatively to the painting or the painting, given that it's set on the mount, it moves automatically, it acquires the next spectral cube, and so on and so forth. So this is how we can acquire lots of spectral cubes in a completely automated way without having to move the instrument. And imagine that each cube takes less than a minute to be collected, so something like around 45 seconds. So you can imagine how fast this data acquisition is. Also here you can see that to speed up even more the data collection, we have a selection of different paintings that we place them one next to the other. So that makes also our data collection even faster. So this is a kind of schematic. Each of these images is one spectral cube, so I'm trying to show a little bit the automatic scanning of the paintings. So as you remember, we said with this, I hope that I proved the time efficiency of this methodology, the spectral imaging using this system. And I hope that you remember that we said that even though the spectral information of this system is not giving you necessarily the pigment identification, but it gives the variation. It can distinguish the different pigments and dyes from each other. We use this data set and for the next step, which is the automatic clustering of large spectral imaging data set using machine learning methods. So why we decided to build our own clustering method? The reason is because before we developed our code, we tried to use the existing methods that were there for the manipulation of a spectral imaging data set. But these methods were requiring pretreatment of the spectral imaging data set, sometimes the interference of the operator in lots of the steps of the treatment, and they were based on algorithms that group the spectral information based on the spectral shape. And these can be limitations because A, you may result with biased results. B, these are methods that cannot be applied on large spectral imaging data set. And when we're talking about grouping of spectral information in the visible regime based on the spectral shape, that can limit your pigment identification. As we know, most of the times when you add white pigments or black inks, the only difference that you have in the reflectance spectrum is changes in the intensity. So if you group if your pigment identification is based only on the shape, you may miss the variation that, for example, this area is painted with azurite or azurite plus white or azurite plus ink. So trying to overcome these limitations, we came up with designing our own clustering method that we want to be unsupervised, constantly updated, unbiased, and being able to perform automatically on large data sets. And the outcome is to go through the large data set and group the areas that are sharing the same similar material composition. So our clustering code is based, just for the ones that are not familiar with the term clustering, clustering means grouping. So basically, we have large spectral data set, and we want to see which spectra are similar. So this is the little schematic of our code with the different steps. Our code is based on the self-organizing map algorithm. It has different stages. We input our data. We do an initial dimensionality reduction. Then we do unsupervised clustering of our data set in order to avoid the bias. And then we have the merging step and a filtering. And then it depends on the application and how detailed we want our clustering to be, we can do further manual merging of the final clustering data set. Just to make the concepts more clear, I would like to use some examples. So you probably remember the scanning of these paintings. These are watercolor paintings belonging to the Moifa and the Get collections. So what our algorithm does is that it goes through them, it finds the pixels that are sharing similar spectral information, it groups them together, and then we get these outcomes of the clustering results, which are what we call cluster maps. So basically here you have some false color images, and each false color corresponds to a specific spectrum. So in other words, we see that through the different spectral cubes, the different paintings as well, there are pixels that are sharing the same spectral information. For example, you can see that the blue area of the first painting, the blue trousers are sharing the same clusters, therefore the same spectral information with the skirt of the second painting. On the third painting, we have different clusters, and on the third, we have other clusters. So we can say that, and also the other outcome of the algorithm, apart from these maps, is the mean cluster spectrum. So you have this visualization of which clusters are sharing the same spectral information, but also you have the spectral information, so which is the spectrum that corresponds to these pixels. Then the third step is to do the multimodal analysis on these clusters and get the material variation and the identification of the different materials that are used have been used in these areas. But also what we find interesting with clustering is that it always, most of the times, it reveals very important information and interesting information that you may have lost if you were not doing clustering. This is a good example of this, is that on the last painting, so the first two paintings, when you do the material analysis, we can see that the blue is made using Prussian blue. The third painting, for the third painting, the blue has been achieved using indigo, an organic blue dye. And on the third painting, the dark blue cluster seems to be a combination of Prussian blue and indigo. And on these paint laws, you can see that we have only Prussian blue. So the assumption that we are making is that the original skirt was painted using indigo, and then there was a loss, and somebody probably retouched the painting and applied the thin wash of Prussian blue. So during this project, the Lima to Canton project, we had the chance to come across with the macro XRF spectral imaging data sets that we haven't analyzed before. So the macro XRF scanner of the Getty Institute is an M6 macro XRF scanner of Bruker. And the traditional way to approach and to analyze macro XRF data set is to extract single element maps. Sometimes people visualize them in false colors. So this way you see where you have the different elements. And if you want to see the collocation between different elements, people usually do create what they call overlaying maps. So basically they select 2, maximum 3 elements, and they co-align the single element maps to see where these 2 up to 3 elements coexist. There are lots of studies that illustrate the benefits of the observation of macro XRF scanning data sets. But these two traditional approaches, we think that they may face sometimes some drawbacks. For example, by observing single element maps, if you have trace amount of a specific element, you may miss it, and this is due to the dynamic range limitations. Because, for example, if you have an area, if we see here the mercury map, which is the red one, you can see that there are some areas that have very, very strong mercury presence. So the whole contrast of the single element map is dictated by the large amount, the areas that contain large amount of mercury. And therefore, if you have an area nearby that has a smaller trace amount of mercury, you're going to miss it because of the dynamic range of the single element map. And also, when we are talking about when we want to see the collocation of the different elements, the overlink maps are good enough, but they go up to 2 or 3 elements. So if you have objects with more complex elemental composition, then it's difficult to see, to investigate in detail the collocation of the different elements. So again, trying to address these limitations, and given that we had our clustering tool, we decided to approach the macro XRF scanning dataset as what they are to us, spectral imaging data sets. Again, you have imaging, you have spectral information, but this time, instead of a reflectance spectrum, you have an XRF spectrum. So we thought that to investigate what and if there are benefits of applying clustering to the interpretation of these kind of data sets. So here, I'm showing you the results of the application of clustering on a painting from the Getty collection, the Fierro collection. So the first image is the colored image of the painting. You can see that probably you're familiar with the clustering map. This is the overall cluster map, but also depends on how you want to interpret your data and what you want to see. You can have also the single cluster maps. So you can say that, okay, you give me a map with all the clusters, but I want to see this specific cluster in which area it corresponds, or these 3 clusters where it corresponds. So that's up to you and how you want to interpret your data. And of course, each of these clusters comes with the corresponding mean cluster spectrum, which in this case is an XRF spectrum. So after we have finished with the clustering of the large collection, we have found the areas that are sharing the similar spectral information and therefore similar material composition. In order to get complete or as complete as possible identification of the materials that are present, what we have to do is to go to representative of each of these areas and apply multimodal analysis using this time our point analytical techniques. So as Haida mentioned, we have traveled a lot, either on our van or taking flights, putting our instruments in suitcases, and traveling around the world. We always start with smiles, then somewhere in between we may cry a little bit, but then we always go back home with a big smile as well. So it's the circle of life, I assume. So obviously, I don't have to explain to you the importance of multimodality. You all know, you're most likely familiar with the different scientific instruments. Each of them have its own strengths, its own limitations, and therefore we have to combine all this together to extract as complete identification as possible. I just want to remind you that apart from the strengths of this and the limitations in the analytical aspect, they all come with some constraints about how, where you locate them. So for example, the XRF has some safety restrictions in terms of the distance of the operator from the instrument. Sometimes we have restriction about the room, the location of the room in a building, the location of the instrument in the building. Raman requires absolute darkness for the data collection. Spectral imaging in the visible regime requires control illumination, so dark rooms that we can control the illumination. FTIR is the easiest one, not requirements from what I remember. So when we visit, we load our instruments, we visit the different institutions. So we need, but also when we leave Nottingham to come to DC or all around the US, we have limited time. So we cannot apply the analysis one instrument at a time. We have to have different workstations that sometimes have to be in different rooms. But as, again, you'll know what we want to do is you want to apply multimodal analysis, but at the same area. So when this is happening in parallel, we want to find a way that we can work in parallel, separately, but also all together. So the latest idea was that we start working using a wireless local area network that allows us to connect our laptops to each other. And then we became more greedy, and we want to have a platform that allows us to do the marking at a time, all together and collaboratively. Flo will, in Florence's talk, she will explain more in detail this new software that we have. I'm going to just say a few things that we can do here. So basically, before each field trip, we always ask our colleagues from the different institutions to share with us photos of the paintings that they think that we should analyze, so we can have an idea about, the differences, which are the paintings, and which is the material variation, pigment variation across the paintings. So with this software, what we can do is that we can upload these images that have been shared from the institutions, or if they haven't shared before, we go and we take some photos with our phones. And then we can add different points that indicate where we collect the data. And here we have different tabs. You can either go to a point, select the point, and add the techniques that you have used to collect data from this specific point. Or you can go, if, for example, I'm collecting XRF data, and I collect data from all the painting, and I want to make sure that I have covered all the points of this painting that are mapped here. I can go and select the specific technique, and then I can see which are the points that I have already collected data, if there is anything missing, and all this stuff. And also here we have the section with the logbook. So for each of these techniques, while you're collecting the data, something may go wrong, maybe your measurement may be interrupted and all this stuff, and you want to keep a record of what happened during the data collection. So we have this section here that you can use, save your logbook. Also, we have the section with the notes about the object. Usually these are archival information about the object, if there is any attribution or this kind of information. So this is about the data collection. And I'm coming to the final point of our workflow, which is the complementary interpretation of the clustering results and all the point analytical data that we have collected for all these clusters. And this combines the use of GUISI, the other software that we developed, and it's a software that we developed for the management of different spectral imaging data set. So after we have collected our data set and we have processed them, we can upload the data on the software. Here you can display the RGB image that derives from the reflectance spectral imaging system, or you can display the different spectral bands, and you can select a region of interest, as you see here, extract the spectrum of the original spectral imaging cube that is displayed here. But also, you can have the visualization of the clustering results. So you can upload your clustering results, And as you see here at the bottom right, we have the section of the clustering visualization. So you can have the overall cluster map if you want, or you can select single and have the visualization of specific clusters. And if you tick these boxes, mean and standard deviation, you have also the displayment here on the plot of the mean cluster spectrum. Maybe it's better to look at this screen. Yeah, the mean cluster spectrum along with the spectral, the standard deviation. So this is a tool that we use for the visualization, but also the evaluation of our clustering results. It's very useful. So this for the spectral imaging data set, then we use the MAPSI. For after we collect our data, we can upload also our data on the MAPSI software. I'm not going very into details because in Florence's presentation, you will see very clearly how we work with that. But we can have the display of the different spectra collected with the different analytical techniques. And also, there is this section here where each of the scientists that are responsible for the interpretation of a specific analytical technique can write some notes about the interpretation of their results. And this, the idea is to have them on the cloud. So everybody, as we collect simultaneously the different data and we update the marking of the data collection, the idea is to work on the interpretation also collaboratively within the scientific group, but also in collaboration also with our colleagues from the cultural heritage institutions. I think that Haida, Fenella have already mentioned how important is the contribution of curators, art historians on the interpretation of the data. So we aim this to be our tool for the scientific interpretation of the data, but also for the collaborative interpretation of the data with art historians and curators of the cultural organizations that we work with in its different projects. So going to the end of my presentation, I just wanted to give some examples of the last part of our workflow, which is the complementary interpretation between the clustering results and the point analytical data. And these are coming from the analysis of the spectral imaging data set that we collected from the Getty collection. So as I told you before, with the visualization of the clustering results, you can do whatever you want. You can have all the clusters together, a single cluster, or selected clusters. So in this example, what we want to see is to investigate what is the material composition of the black scarf of this figure. So what we saw is that this black scarf is represented by 3 clusters. All of them were sharing the same spectral information, and their only differences were in the intensity. Before we spoke about the intensities in the reflectance spectrum, but also in the XRF, it probably indicates differences in the concentration or the thickness of the paint layer. So we think that it is about the thickness of the paint layer, as you can see that the outline that are represented by the light pink cluster, you have a thicker application of the black substance that was used to paint the scarf. It was interesting that, as you see, all these areas are heavily dominated by the presence of lead. So most of the people, when we see lead, we think about lead white, red lead, massicot, this kind of pigments. What we saw when we did the multimodal analysis is that Raman was giving us only carbon black and some traces of vermilion, and no presence of lead white or red lead. That was quite interesting because all these pigments are quite good Raman scatters, so not seeing them, it was quite strange, and it was like, what is happening? Also, the microscopic images showed us we couldn't see really any yellow or white particles in these areas, and it was also strange because you have very strong lead. Then the next idea was that this black may contain some other lead-containing substances like platnerite or galena. And again, here at the bottom right, you can see that we have the spectrum, the force spectrum of that we collected from this black area. And we plot them against the platnerite, which is the red spectrum, and the galena, which is the blue spectrum. So we can see that it doesn't agree with any of them. So we excluded even these lead-containing pigments. So our result is that this is a lead-containing ink, which was very interesting because I tried to find, I was like, this is lead ink. And I tried to find any reference of lead ink. And the only thing that I found so far is the presence of lead ink in some pari, which is historically, it's a little bit strange, but it is a lead-containing ink. Another example is, we found that it's interesting, is about the pigment identification of the green skirt of the lady. And what we saw, also applying Raman analysis on these areas, is that what is interesting is that when your analysis is based on single element maps and only on one modality, the conclusions that you may extract can be misleading, because you have lead here, for example, chromium, barium, all this can be different pigments. It can be lemon yellow, it can be lots of different pigments. So what we found for the green skirt is that it was made by a combination of chrome yellow, Prussian blue, and carbon black. And the difference between these two clusters is that at the darker areas where the dark blue cluster is found, we have a higher signal of lead and vermilion. So we think that the green skirt was made using a combination of chrome yellow, Prussian blue, and carbon black. And at the shade, the darker areas, the mixture that we found also on the scarf, the lead-containing ink with vermilion, was used. And the final example to show the importance of the clustering and the spatial distribution of the different clusters, not only for the pigment, it comes not only to the pigment identification, but we can see that clustering allows us to see things about the paint sequence as well. So as you can see, at the edges of the apron of this figure, we could see that we have the presence of 3 clusters. I don't know if it's obvious. Here, on the second image, we have the collocation of 3 clusters. So we try to find what is the correlation between these 3 clusters and why they're all together. And what we saw is that cluster 10, that corresponds to the light blue areas, has a strong presence of iron, but also barium. And in the Raman analysis that we performed in these areas, we found the presence of Prussian blue. And on the other hand, cluster 8, which corresponds to the red cluster here, contains lead and vermilion. And we assume that it's, again, the combination of this lead-containing ink with vermilion. But what we saw is that in between these 2 clusters, we have areas that spectrally, in the XRF spectra, is a combination of these two clusters. So they have, it's the combination of these two clusters. And when we performed Raman analysis on representative of these cluster areas, what we found was a combination of Prussian blue and carbon black and some particles of vermilion. So we saw, and then we went to do also close optical microscopy. You can see that the presence of these three clusters has a reason, and it indicates the paint sequence. So firstly, it was applied the light blue area, the light blue frame, and then on top of it, it was applied the highlight that was made using a mixture of lead containing ink and vermilion that sometimes was overlaying with the blue lines. So by going through all the clusters and doing this complementary analysis, we managed to get the palette of this painting. And that's it from me. And thank you very much. I don't know if now...
Thank you, Sateria. If I could ask Haida to come up as well. I believe we have one or two questions online, and what we'll do is we'll repeat them so that others of you online can hear them as well. If you could come up to the microphone, Chris. Thank you.
Hi. Okay. Hi, thanks for the talks. So we had one question so far online. The PRISM system was extremely interesting. There was some query about whether you'd consider expanding the wavelengths, particularly into the UV.
Okay. And so I wondered when they asked this question whether they mean to expand to UV in order to do reflectance spectral imaging, or is it for fluorescence? But okay, I will answer to both. So if it is for reflectance, for fluorescence, okay. So then, for fluorescence, you can already do it. You just change your light source. You don't use your tungsten light. You can use a UV LED or whatever in order to, in fact, we already do laser-induced fluorescence hyperspectral imaging. In a remote mode, I talked about it, but you can also do it close by. So you illuminate, because if you do the laser, you don't need the filter, right? You only illuminating in the UV part, and you can expand your beam, laser beam, so that you illuminate an area, and then you just use your normal hyperspectral imaging system to collect the data to get the fluorescence spectral cube.
I have to say that I tried it also with prisms, and it seems that it works. So yeah, it's a good goal.
And probably it's more sensible to do it with the lower spectral resolution, because usually the fluorescence signal are broad in its spectral response, and then it's easier. Yeah, that's right.
So then a follow-up is, do you use an achromatic camera for your normal MSI system?
Okay, let me be very clear about this. The word multispectral imaging used to mean something the same as hyperspectral. It's just a smaller number of bands. But more recently, the conservation world has adopted the word MSI, multispectral imaging, to mean something quite different. Because I hear people say, okay, I have a MSI system, meaning that it can do fluorescence, it can do what we normally think about reflectance spectral imaging. So it's all mixed. So you're not dealing with one modality anymore. And because of that, I've abandoned the word MSI for what we do, because essentially it's all spectral imaging, reflectance spectral imaging. So with reflected spectral imaging, I think the question is about whether we use monochromatic camera or not. Yeah, of course, you use monochromatic camera, yes. And then just with a filter in front for that particular system.
Do we have questions from the audience?
We were very clear. No.
Great talks. Just wanted to say that up front. Really informative. I'm not as familiar with reading OCT maps, so Dr. Leong, I just wanted to ask you to just kind of go through, I guess, like what we were supposed to look for when you were looking at the paintings at the National Gallery, as well as for the pith. It was harder for me to figure out.
Yes. Yeah, it's not usually not immediately obvious, indeed. So let me just go back to that and find my slide on that. I think it's somewhere later on in the okay, here is the National Gallery one. It's got lots of cubes going on. And so, is that the laser? Laser pointer, yeah? No.
Yes.
So how
If
you
you
do it?
click here.
Ah, right, okay. Right, so maybe I want to stop this. Let's stop.
It will stop at this.
Okay, so what happens is that, look at this one. You have this very bright line at the top, yeah?
Do you want to say that this cross-section, cross-section?
Yeah. So we collect the data cross-section, point by point, like this. Okay. So therefore, what you're getting, the top, this line is the interface between air and varnish. Okay. So it's not a layer; it's an interface. And then below that, you see the dark patches. That means that there's no scattering. When there's high amount of scattering, it's very white. Okay, so there's no scattering, which means either everything's absorbed or it's transparent. In this case, it's transparent, because if everything's absorbed, you should not see anything below that layer, right? So I know that's transparent. That's why I don't see photons coming from that layer. Yeah, and then below, I see again some undulating features. That's quite white and therefore highly scattering. And that you can actually sometimes see another layer of varnish here, another interface, yeah, in the grooves in between the brush strokes, yeah. And then you have, for example, here the paint layer, yeah. And then this one is a very odd painting from the National Gallery, because it was painted on some kind of board, wooden board, furniture type. It used to be furniture, I was told, and which has its own coating, the original varnish from that. And then on top of that, they were painting different paint layers and so on. So you see loads of layers there. And so that one, what we've done is that we've mosaicked a number of such image cubes together. And now you can see a bigger image cube. Because OCT is a microscopic technique, so if you have to achieve high resolution, then necessarily your field of view is smaller. And so in order to be a bigger area, you've got to mosaic them. And so that's what you're seeing there.
The mosaic is very distinct, and I was just curious about
the layers, yes. That's always what people ask. Yes.
Maybe you want to explain a little bit again how do we know that we have a back paint? With the pith.
Right. Okay, yeah. I didn't have this very important laser point. And now I have that, it's easier to explain. So this is, again, a virtual cross-section. So the OCT is like a couple centimeters above, yeah, the probe. And then you're seeing, this is the pith, with all these cells you're seeing, yeah? And below that, you see that on this side, so it's a cross-section along the yellow line, yeah? So when you're outside of the painted frame, what you have just plain pith with, again, black, meaning it's transparent, and then below the scattering, which is the backing paper. Yeah? And on this side, on the other hand, you see something different. There is another scattering layer there, which is to do with the back painting. See, because you have a reference difference here. And then that's the entire cube. Yeah?
Thank you so much.
Okay.
Any other questions?
Thank you. Hi. Really informative. Just wanted to sort of ask if you could talk a little bit more about how your organizational model for the AI and the automated sort of organization of the paintings and all the other information, how you're making it, you said, I think, equitable, I think was the word that you mentioned.
Sorry? I didn't hear what you said.
Oh, the organization of the images that you're creating sort of like the database for. You mentioned that there is a process of automation in how you're organizing the clusters and all that other stuff. And I was wondering how you were making that, I think you said ethical, maybe. I don't remember the exact words that you used.
I'm not hearing very well. Ethical.
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 They might
Yeah.
need available.
Yeah, I guess available to the public or anything like that, how your AI organizational model is sort of
Okay,
working.
Okay,
Yeah.
okay. I think I got what you said. So just be careful here. We are not doing the kind of AI that cause ethical issues there, because for a start, this is more machine learning than the sort of AI people talk about. And so. And what we do is actually not the kind of deep learning type where the machine is learning from humans. It's actually learning from the data. It's a shallow learning process. And so you are basically, but we still have human in the loop to check everything's correct, if that is the angle at which, or maybe the
But also the human takes, not based on their biased opinion, what is what, but always going back to the original cube, if that makes sense. So sometimes people talk about machines are going to replace humans, and then the other argument, it's like humans are irreplaceable, they know the truth and they are stronger than the humans. My opinion is that nature and spectra are above all of us, because we are biased. The machine is something that we train to use. So you always have to go back to the truth, which is the spectral information. So, yeah, I don't know if I answered to your, it was close to relevant, yeah.
Any other questions? So if you could just join me again in thanking both of our morning speakers. We're going to take a break from 12 to 1. For those of you online, please stay online and come back at 1 o'clock. And we will look forward to our 2 afternoon speakers. So thank you for joining us, and please come back at 1 o'clock. So I want to welcome you all back to our afternoon. 2 more presentations from our team from the University of Nottingham-Trent. And first speaker this afternoon is Dr. Jake Hollis. I will hand over to him. Thank you.
Okay, yeah. Not quite a doctor yet, but getting there. Hi, I'm Jake, and this is a presentation on the latest developments in automated analysis of macro XRF spectral imaging datasets using statistical methods. So, over the past few years, there has been drastic advances in image capturing technology, which then leads to an ever-increasing amount of image data being captured. So from that amount of image data being captured, we end up having a more and more increasing demand for analysis to be performed on that data. So some of the stuff that we want to bring forward is the automation of analysis, so that users can be allowed to conduct their own analysis on their data via the process of automation. So then this would then be allowed to reduce the number of human hours required by the process of manual analysis. So instead, you could set up a few image cubes to analyze overnight and let the computer run overnight so that you don't have to perform that analysis throughout the day. So in order to do this, we'll be introducing some statistical methods in order to help develop and improve this automated process of analysis. So 2 of these areas will be techniques for addressing noise effectively, as well as developing the clustering algorithm that we currently have. So looking at the data, there's 2 sets of data that we're going to be using today. This is the first set of data depicting a Peruvian man. This was captured by the Getty Conservation Institute using the Bruker M6 jet stream with an integration time of 25 milliseconds. And the XRF cube itself has dimensions of 276 by 569 with a spectral dimension of 4,096 channels. The second data set was collected by the National Museum of Asian Art, and this is a New Year's assembly of items. This was captured using the Amtech XRF scanner with an integration time of 200 milliseconds and an XRF cube having dimensions of 550 by 661 pixels and a spectral dimension of 2,048 channels. So when we compare a single pixel spectrum from each of the image data, we can see that there's quite a significant difference in terms of the signal-to-noise ratio. So this will allow us to show the capability of our processes to work on both lower and higher signal-to-noise ratio data. So a little introduction into the clustering process. So as mentioned previously, our clustering algorithm utilizes something known as Cohen's self-organizing maps. What this essentially does is takes all of the pixels of our image data and groups them together into groups of similar spectra, essentially. So you'll have a number of different clusters, and within each of those clusters, there will be corresponding pixels, each sharing a similar spectra to one another. So here's a single cluster map output from the New Year's assembly data. So I've highlighted here 2 different spatial regions, as you can see. And when we look at the spectra, we can see that particularly in the Mercury peaks here and here, we can see that there's a difference between the 2 spatial regions, and these shouldn't be merged together. And looking at the Peruvian man data, we can see also within these 2 spatial regions that there is a difference within the Mercury peaks. So these shouldn't be merged together either. So one of the first processes that we started with was looking at addressing noise within the data. So in order to do this, we utilized the discrete wavelet transformation. So this is a process that reduces the dimensionality of the image data, specifically the spectral dimension. We prefer this over other techniques since it preserves the local features of the signal, so it keeps those peak informations that you see in the XRF spectra whilst reducing the dimensionality down. So this allows us to run our clustering algorithm at a much faster rate without losing any of the cluster quality. Here's a little diagram of how this operation works. We essentially start with our original signal and then utilize a transformation matrix that then produces a signal approximation and then continues to do so for a specific amount of times. You can provide it with a number of times to perform this decomposition. So for instance, with the 4,098 channels, we could decompose it 4 times down to 256 channels. So the next thing that we wanted to make sure was that there wasn't any anomalies within our data when performing the transformation. So what we've done here is selected a 50 by 50 region of fairly uniform spectra, so taken from the background, and taken a single pixel, if you can just see here, this blue pixel here, And we've attained this single pixel and performed the wavelet transformation to it in order to compare both the 50 by 50 region mean spectra to the wavelet transformed single pixel spectra. And what we can see is that we haven't introduced any anomalies into our data, so that's great. So then we can carry on utilizing this transformed data in our analysis. So to look at the clustering comparison, we've taken just our standard image cube data and our wavelet transformed data and looked at corresponding single cluster maps. And what we can see here is that within these two spatial regions, there's a difference within the copper peak. A difference between the copper peaks, whereas in the discrete wavelet transformed data, we don't have that difference between the spatial regions. However, when we look in different cluster maps of the same corresponding object, we can see again that difference within the Mercury peaks are still apparent within the two separate spatial regions. And, looking at the Peruvian man data, we can see similarly where these two spatial regions were clustered together in the original data, but had a difference within their Mercury peaks. But when performing the discrete wavelet transformation, we can then see that these differences between the peaks has gone. However, the improvement on the signal to noise isn't as drastic enough to the point where we can smoothly and cleanly handle all of our data, as we still end up with these points where, whilst this is a slightly small difference in manganese, we can see that it's still apparent between the standard and the discrete wavelet transformed. So on top of the discrete wavelet transformation, we then began to look at spatial spectral clustering. So what this means is that we would take our spectral cluster maps and perform a spatial clustering on them. So we will group together the pixels that are in similar spatial regions. So for this, we use a connected component labeling algorithm, and what this essentially does is just look at which pixels are neighboring each other and labels them into a single group. So we can see where there's different regions, these different colors correspond to different groupings of spatial clusters. When looking at the clustering comparison, we have here our no spatial spectral, so this corresponds to just performing the discrete wavelet transformation and then clustering, whereas this is performing the discrete wavelet transformation as well as performing the spatial spectral clustering on top. So what we can see here is these two spatial regions here show a slight difference within a lead peak, whereas once we perform the spatial spectral clustering, we're able to remove that area from the cluster map and thus have a much cleaner spectra among the spatial regions. However, again, within these two regions, we're again seeing a difference in the Mercury channels. So from this, we understood that it could possibly become an issue of how our clusters are merged together. At the moment, they were currently merged together on the basis of being a standard deviation apart from each other. So the cluster means of one area would be a standard, if it was within a standard deviation of the other cluster means, they would be joined together. So I'll move on to the Peruvian man data. Similarly, we have the shirt and trouser region in the non-spatial spectral clustering, showing a minor difference within the manganese channel peak, and then looking at the spatial spectral, we've lost that area of the trouser, and looking at the shirt, we just see a nice smooth spectra. However, looking at a different cluster map, we can see that it's maintained these two spatial regions even when performing spatial spectral clustering, and we still have that apparent difference within the manganese peaks. So the next stage, on top of performing the wavelet transformation and spatial spectral clustering, is then to look at a different method for merging our clusters together. So the new method that we've introduced is a statistical distribution-based merging. So this is based on the foundation that two spectra sampled from the same population should follow the same distribution. So to elaborate, that would be 2 pixels containing the same elements should follow the same distribution within their spectra. So in order to compare the distributions against each other for each cluster, we use the 2-sample Kolmogorov-Smirnov test. So this is a statistical test to test 2 different distributions against each other to see whether or not they follow the same distribution or a different distribution. And one particular advantage of this is that it doesn't assume any distributions prior to performing the test. So that allows us to introduce any sort of distribution into the test without it having any negative performance on the actual test outcome. When looking at the clustering output, we begin to see much more positive results. So here we have just performing our wavelet transform and spatial spectral clustering. We can see within the 2 spatial regions, we're having that difference within the mercury peaks. But when performing the distribution-based merging rather than standard deviation-based merging, we begin to see that it's isolated this particular region and doesn't cluster it together with the region that had the mercury peaks apparent. So this allows us to produce much more concise and tight clusters. And whilst this does increase the number of clusters that we produce, we know that these clusters are statistically different from one another. So then we're essentially attempting to reduce the number of false merging as to a minimal amount as possible. When looking at the Peruvian man dataset, we can see here that using the spatial spectral with the discrete wavelet transform, we have our 2 spatial regions with a difference in the manganese peak. And then when introducing the distribution-based merging, it's isolated this region to itself without clustering it together with this region that had the difference in the manganese peak. So to conclude, we've introduced the discrete wavelet transformation in order to reduce the spectral dimensionality of our data and address some of the noise within that data, as well as presented a spatial spectral clustering algorithm in order to further address the noise within our analysis. On top of that, we've managed to introduce a statistics-based process for merging our clusters together based upon distribution similarity, and then shown the advantages of using this clustering with these methods. In the future, we'd like to look at using more advanced techniques for our spatial spectral clustering, as well as further developing the statistical distribution-based merging. Thank you all for listening to my talk. So I believe next we have Florence. Yeah.
Thank you so much. And any questions that haven't come through online yet, we'll take at the end of the next presentation. So I'd like to invite Florence. Sorry, I don't have my glasses on, so I can't see the screen. Thank you so much. Hand over.
Okay, so my talk is more covering one particular case study using our heritage materials research platform that was outlined earlier on by both Heide Liang and Satiria Kogu, which includes the digital tools described and also the workflow in general that's used for this kind of pigment analysis. So this is looking at watercolors from the Library of Congress. So the work carried out for this is part of a larger project, which we've described earlier in previous talks, called From Lima to Canton and Beyond. And this involves many different collaborators in different institutions, and these are across both the UK and the US. and I'll just be focusing on the collection from Library of Congress. So in terms of the collections here that were measured by our lab and by the staff here, we covered a number of different collections. These are all watercolours and all part of this broader project for Lima to Canton and beyond. And for the purpose of this talk, to outline the workflow, I'll be focusing on the costumes of the people of Peru collection. So here's just a number of paintings within this particular collection. There are 36 in total. So what's interesting about these watercolor paintings, which was touched upon earlier, is that the drawings are attributed to Peruvian artists with the style and subject matter attributed to Pancho Fierro. So these are Peruvian, but these are on top of pith paper, which is typically Chinese. And then the watercolor paintings are attributed to the Tsinghua studio based in Canton. So these are Chinese watercolors with Peruvian drawings. And this is just a painting of this particular studio in Canton, just to get an idea of them and these different artists creating export paintings of this particular type. So to analyze this collection, we used a number of different techniques. So this includes spectral imaging in the visible to near infrared, X-ray fluorescence, Fourier transform infrared spectrometry, and fiber optics reflectance spectroscopy, as well as a portable Raman system. And here are some images of data collection at the Library of Congress. So what was good was that people from because the Library of Congress already has plenty of resources here, a lot of the data could be taken by the Library of Congress, although typically we would take all of these kind of techniques with us. So the workflow was described earlier by Soteria Kogu. And so in this case, I'll just go over again what the workflow was in particular at the Library of Congress. So we had spectral imaging carried out of the watercolor paintings using a Megavision system here at the Library of Congress. And then image calibration and processing was carried out. And then once we have our calibrated data, we're able to apply an unsupervised machine learning method, and this is using Cohen's self-organizing map. And then once we have, we apply this clustering in order to get the spectral information across different paintings. And with this, you're able to map material differences across the entire collection. And then we use this information to then work out where we should apply our point analysis. So once we combine all of this information, the clustering and the point analysis, we can then apply a further step, which is to model the reflectance that we see for a given cluster based on all of the information collected. So this was applied to the Peruvian paintings collection. We had 36 spectral images. These were clustered. And then the process that I would go through for material analysis is to check the spectral imaging, using some of the digital tools that we were covered earlier in a previous talk. So we have GUISI, which is for spectral imaging in particular. And then using this cluster maps, we can go in to try and find point analysis data which falls within a given cluster map that we have visualized previously. And to do this, we use the MAPSI software, which enables us to map as well as to upload data and visualize these different data sets across a given collection. So then, based upon this analysis, we can test our hypothesis for a given pigment mixture. So just to firstly give an example, this was one of the first paintings, painting 1. And on the left, we have the color image, which is produced from the visible to near-infrared spectral imaging. And then we have the cluster maps on the right-hand side. So you can see there are a number of clusters mapped across different paintings. These are just a few for an example. And the blue cluster here is mapped across different paintings. So then what I would do is to go into this software to enable me to check where exactly these clusters are for a given cluster, where we find spectral similarities and therefore probably the same material composition. So for this blue cluster, we can see that here, how do I get the? Yeah. So here is the cluster map. We have the blue cluster map here for a single cluster, and then the mean spectrum for a given cluster on the right-hand side as well. And we see that this cluster is distributed across different paintings. So then I can go back to check the point analysis to see where we have taken point with different techniques within these areas that I've just found. So just as an example here, we have, for example, these points taken in the blue area corresponding to the blue cluster. And we have force measurement. And we can see from this characteristic lines attributed to azurite. And then we can change techniques and check what more information we can get. So what we find with the XRF for this same point is that we have both copper and iron. But depending on the point, so we have a darker and a lighter blue area. There's different ratios of copper and iron depending on how dark or pale this blue is. So as you would expect for azurite, we have this strong copper for the light blue area. And then for the darker areas, we have stronger iron. So I'd be keeping notes as I'm looking through this data set, and what I'm thinking now is, where does this iron come from? Because we expect the copper from azurite. So we can check further techniques. So in this case, the FTIR for Prussian blue, which is iron containing. And we see lines characteristic of Prussian blue, and also this is for the darker area of blue. We see weaker lines for the azurite. So this is what we expect. So given all of our results, I then go on to try and model the reflectance data for this given region, or this cluster. And we see that azurite mixed with Prussian blue gives a good Quebec-Monk fit. So we can then say with some confidence that this is the pigment mixture for the blue areas. And again, we can make notes, and whoever's doing the analysis can be applying these notes within this area here to add in for each technique what you think the pigments are as you go along, which can then be shared with collaborators. So moving on to a different cluster, we can look at the green cluster. And again, we have the color image on the left and cluster maps on the right. And we see the green cluster mapped across different paintings. So again, we can see where these areas are in terms of different paintings. So just to fast forward, this is where I would have made my notes about the different techniques for this green cluster. What we find is for this cluster a spectral signature with force, which corresponds to malachite when we compare with our reference database. And with XRF, we see copper, as expected for malachite. And again, we have this iron contribution in the XRF. So given previous results, we can test the hypothesis of Prussian blue being a kind of darkening pigment. Because when we try to fit with just malachite alone, this is our fit, but when we combine with the Prussian blue, we see that our fit is very good with this mixture of malachite and Prussian blue. So this suggests that Prussian blue is applied throughout the painting as a darkening pigment. So this process is followed through for all kinds of different pigment mixtures, and these are just some of the results that we found for this particular collection. So the blue and the green we've mentioned previously, and then for brown areas we found a mixture of red ochre and indigo, and this was based on first by looking at the force spectral signature, which seemed to have this indigo high reflectance in the near infrared. And we also have the iron contribution from seen in the XRF. So we would think for a brown, this could be ochre. And we found that was a good fit as well. For the red cluster, we found vermilion throughout, because we have this mercury, which is indicative of vermilion, found throughout the paintings. And it's when we were able to combine the XRF with the force data that we're able to see that there was also an addition of scale insect dye based on absorption bands seen at 525 and 560 nanometers. So you can see how important the multimodal analysis is. And what we found interesting as well is for the black or the darkest areas, particularly in the shawls and the headdresses, we find a higher concentration of lead, which links again to different collections. So Soteria Kogu mentioned previously that in the Pancho Fierro collection, she found also this higher concentration of lead in darker areas, which is unusual. You would expect if it's a lead white, there's a higher concentration for paler areas. So again, this might be interesting because this may be a link between the pith-based Chinese paintings and the materials used by the Peruvians. And this data analysis is ongoing. Thank you for your attention. And hopefully I've managed to demonstrate the kind of workflow that we go through with our pigment analysis for different collections using this case study.
Thank you, Dr. Liggins. Jake, if you'd like to come back up, and maybe Haida and Soteria could come to the front. Do we have any questions for our afternoon speakers? We have one from online, and Chris will share that.
Hi there. Thanks for the afternoon presentations. I believe this question is specifically referring to, towards Luke's presentation. Does the KS test therefore help with the cluster merging based off matrix effect, e.g. more or less than Bremsstrahlung? I'm sorry if I butchered that. In other words, is the statistical approach allows you to skip a pre-processing step like normalizing XRF spectra to the Compton peak?
I think we probably need to repeat again because it's very long.
Yeah.
Sorry. Thank you. Does the KS test therefore help with the cluster merging based off the matrix effect? Does it allow you to skip pre-processing steps like normalizing the XRF spectra in the Compton or to the Compton peak?
Yeah, so we don't normalize the XRF data anyways, so we wouldn't, in that sense, we wouldn't have normalized, so yeah.
So the wavelet, discrete wavelet transformation is our pre-processing process. Basically, it shrinks the data down to all the channels with information.
But yeah, we avoid also to do the normalization because, again, we are interested in the intensity differences because that imply maybe differences in concentration and all this stuff that we are interested in.
We want to keep all the information.
Nothing. It was just a simple addition that we avoid to have any normalization of the data because, as we said also before, with our code we are very interested in the intensity also differences that may imply differences in concentrations and all this stuff. So we want to keep the whole information there. And as you remember, probably we said that depending though on the case study, we have the final stage that allows you to do manual merging. So if you decide that you only care about the elemental information and not about intensities, you can merge the clusters.
Yeah, and in addition, because whoever it was mentioned matrix effect, right? I mean, we are keeping that as well.
You've started to tease us and tantalize us a little bit with some differences and intrigue, and I know it's ongoing. Is there any surprise or unusual thing you've found that separates location? Or it's interesting starting to see the different studios too, and I'm wondering if you can separate studios in the same location potentially or not.
I don't think we have an example of different studios at the same location, but we are trying to sort of distinguish, for example, the Chinese export painting versus the paintings for domestic consumption. But there are surprises like what Florence just showed. You wouldn't expect the way they use this very special ink with lots of lead in China and in Peru. That is actually just something we found out a day or two ago, right? And we're just wondering what's going on. You know, we need to look at the other collections that we've got and see if we see similar sort of things or not, like the Sanhua one, which has Chinese subject. Do they also use lead-based ink? I doubt it.
I also had a question for Jake, and that was whether the order of operations of the different techniques that you're using matters, and that is especially since you got such a difference by tightening the automatic merging. Can you do that and skip the spectral spatial step, or do you think you need them both, or are you planning on testing that?
It should, in sense, follow in the order because the wavelet transformation essentially acts as a pre-processing form on the data. And then from order of operation, you initially start off with clustering, so you have spectral cluster maps. You then essentially break down those spectral cluster maps into spatial regions and then merge them based on spectral again, but with using a tighter distribution-based format. So I don't believe you'd be able to swap, say, the distribution merging and remove the spatial aspect completely because you'd just be essentially merging two large spatial regions based on their spectral properties.
And also, I guess it's the SOM is not completely deterministic as doing a non-parametric statistical test between two samples. You ask the question, are these two samples from the same distribution or not? Yeah, that's a yes or no answer, right?
Another a little bit long one. Is the KM fitting something you're doing in one or both of the software tools that you're developing, GUSI and MAPSI? I'm curious how you're implementing the fitting. By the way, I'm very excited about both GUSI and MAPSI, and will definitely be watching this space. Thanks for working on the tool to share with the community.
Do you want to go for that? I think that's not really for Jake, that question, or you want to?
Yeah, or if you want. Anyways, yeah, KM, currently we do it in using...
No, we're not talking about KM. They were just wondering whether the GUSI and MAPSI, how does that, is it?
They're implementing KM.
KM.
Something
Yes.
you're doing in one or both of the
Oh, it is
softwares.
KM, okay.
Yes.
I thought it was GUSI and MAPSI.
No worries. Yeah, so KM, currently we do it using an individual code, but the ultimate goal is to put KM also on MAPSI, and we have lots of ideas about, because we have lots of individual little codes for processing of the different modality spectra. So the idea is to incorporate everything on MAPSI, correct?
Yeah, conversion.
And then the question is also whether, we have a big debate, a long debate in the group, whether we even want to merge GUSI and MAPSI and how we want to go through things. I guess that this is something that we would like also to discuss with the broader community once we manage to bring both softwares in the level that we feel that we're confident and we're happy with. It would be nice to talk again all together and see if we want to have one big software that does everything, or we want to keep them separately, what other modalities we want to add, and all this stuff. So. Already, I think that yesterday's hands-on, we had a hands-on workshop yesterday at Freer Gallery about these two softwares, and it was very useful for us, all the feedback.
Yes. Yeah.
It's kind of something, on the way here we've been debating, we flew on the plane, and when we met up with the rest of the team, we kept on arguing with each other whether or not we should do this or that. And it is really you guys who help us, having your opinion, and help us decide which way to go.
We had another question come in about MAPSI. To start off, they said, thank you for the exciting presentation. They were curious about the other types of analysis, how in UC you could see the individual analysis, if those can also be integrated into MAPC. And if MAPC may be compatible with existing software already, or if it will be compatible with existing software.
So you just have to make sure that you convert into the correct formats, because obviously with certain softwares, you're given spectra which you can only use in those particular softwares. So with different codes, we have conversion of data into different formats that we can use in MAPC. What was the other part of the question? Can you introduce a new technique? Yes. Yeah. So if you have a spectrum, it can be any spectrum, and you can add that as a technique. If it's in the correct format, you can upload your data set, you can describe your new technique. So that should be fine. And we were even mentioning yesterday, if you did microscopy, for example, you could include that market where you've taken microscopy and then store the images as a data set within the data structure that's created by the project folder. So the information and the images would be there, and then a next step would be to perhaps display these kind of image data sets as part of this.
So instead of the spectrum, you can have the microscope image out.
You could just have an image, or two,
I just want to say that I think our colleague who wrote the code for MAPC, who had just arrived in the lab recently from Mexico, and she is listening here, and so we should actually thank Andrea, who wrote the software.
Yes, Andrea. She's on the thanks, yes.
Yes.
Two more questions. One is a number of institutions do not have unlimited access to data storage, and I'm just wondering, is there any capacity limit in terms of the software, the platforms that you've set up, and ways around that? And the other question is more just a curious one, like what's the next instrument you really want? You know, you're going to start adding an OCT, so those are my two questions.
Okay, I'll take that. First of all, when you talk about the data storage, well, I mean, these GUIC MAPC doesn't need very much. It's a data that is linking. That's the issue, I guess. I mean, for us, for example, we can use our cloud or our internal server. At the moment, clouds are very expensive. When you, unless you do cold storage, it's cheap. But if you keep on having to interact with it, it's very expensive, which is why we try to limit ourselves, if we're working only within the team, to use our own lab server. And in fact, we do that just before coming. Flo and I were both at home, and then the data was on the server. We were both trying to get through onto MAPC to interact. So Flo might write something, I think this is whatever, you don't even need to talk to each other. But one thing, maybe, I don't know whether that was clear to everyone or not. So we're going to Hispanic Society America tonight, and tomorrow we're going to start collecting data. And there we would be in different rooms, as Sochira showed, and we will have actually a laptop in the middle that would be holding the database as we collect and as we, it's acting as our internal server. And we don't actually need to necessarily access your Wi-Fi to be able to do that. So that's one part of the storage, I guess.
Part of it was just a little bit of a push for funding agencies to sort of do a bit more support for smaller institutions who don't have the ability to leverage, if they're an institution. So just sort of throwing that out there into the ether.
Yeah, and also we encountered the issue that, people think, institutions think about capital, but cloud access, they don't know how to deal with that sometimes. you buy it, and then they say, end of the project, you have to use it all up. No, but I want you to keep using it. And that kind of thing, I think people haven't come around to how to resolve these kind of issues. That kind of depends on the fiscal rules as well. And I don't know what it is like in the US, but we have this kind of issue. Okay, yeah. And in terms of what the next instruments, well, at the moment in the lab, just before I left, I think we had an intern working with one of our PhD students. They've just successfully developed offset OCT that could see deeper into the layers. Oh, that's one example.
So building off Vanel's question, NMAA has an extensive suite of scientific equipment. Based on your work there, did you identify any challenges, opportunities, other than you might have just described, integrating data from additional instruments that you may not have been accustomed to already?
You mean, do they mean using the new instruments from NMAA? Well, I mean, after we went back, so last year after we went back, they had installed all these suites of what I think it all fall into the spectral imaging category, right? Basically, spatial dimension plus a third energy or spectral direction, right? So they had this, and so they were able to then collect this data and send it to us, and then we process them. And I don't think that was any
Jake's
issue.
presentation, it was...
Yes, based on, it was just recent, like 3 weeks ago, wasn't it? That Matt has scanned a couple of paintings and sent it to us, and Jake just processed them and presented them.
No problem.
Yeah.
No.
No. Data is data. As long as you know the key to decode the data format, that's all it matters.
So I just want to thank everyone for the wonderful questions and our colleagues for the great discussion. We're really looking forward to, I was talking earlier with Catherine, we're thinking like the next symposium is really starting to talk about some of the different platforms we're developing and what's that base level of interoperability that we can start to engage and interact more. So thank you all again. If you could all join me in thanking our colleagues again.